Good day, viewers. We shall begin by looking at Rn from a viewpoint wherein we look at elements of Rn as vectors. Our approach shall be not that of physicists who start looking at vectors as entities which have direction and magnitude. We shall also not adopt the pure axiomatic approach either. Our approach will be quite informal in the sense we only want to appreciate that some of the important properties of Rn are taken as the defining axioms in the definition of vector space. Vector space operations. Note that two elements x equal to x1, x2 up to xn and y equal to y1, y2 up to yn in Rn are equal if all the corresponding coordinates are equal, that is x equal to x1, x2 up to xn and y equal to y1, y2, yn are equal if and only if xi equal to yi for all I equal to 1, 2 up to n. Suppose x, y, z are in Rn and alpha, beta are in R, and if the operations are defined as x plus y equal to x1, x2 up to xn plus y1, y2 up to yn equal to x1 plus y1, x2 plus y2 up to xn plus yn, and alpha x is equal to alpha x1, alpha x2, alpha xn. That is, operations defined this way are called pointwise defined operations. They are called the addition and scalar multiplication. These operations have the properties 1. For each x y in Rn and alpha in R, x plus y is in Rn and alpha x also is in Rn. 2. For each x y z in Rn, x plus y plus z equal to x plus y plus z. This property is called associativity. 3. There exists element 0 equal to 0, 0 up to 0 in Rn with the property that x plus 0 equal to 0 plus x equal to x for all x in Rn. 4. For each element x equal to x1, x2 up to xn in Rn, there exists element which is denoted by minus x equal to minus x1, minus x2 up to minus xn in Rn such that x plus minus x equal to 0. 5. For all x y in Rn, x plus y is equal to y plus x. 6. For all x in Rn and alpha beta in R, alpha beta x equal to alpha beta x 7. For all x y in Rn and alpha in R, alpha multiplied by x plus y equal to alpha x plus alpha y. 8. For all x in Rn, alpha beta in R, alpha plus beta x equal to alpha x plus beta x. 9. 1 x equal to x for all x in Rn. With this algebraic structure, we say that Rn is real vector space or real linear space, or simply vector space or linear space. The elements of Rn are called vectors and the elements of R in this context are called scalars. The two operations are respectively called vector addition and scalar multiplication. Any system wherein there are operations similar to operations just considered and which satisfies all the properties just mentioned is also called a vector space. That is, any set V on which there are operations similar to those in Rn that satisfies the properties 1 to 9 is called a vector space, and elements of V in this case are called vectors. Geometric representation. Given a point x in Rn, often we look at x as a directed line segment from origin towards the point. When two vectors x and y are in Rn are given, one can show that the sum defined earlier is the same as finding x plus y by completing the parallelogram. That means that at the tail of x put a directed line segment which is parallel to y and is of same length as the length of y. This is called a parallel translate of y. All these are shown in the figure. The scalar multiplication alpha x is interpreted as the vector which is in the same direction or the reverse direction depending on alpha being positive or negative. That is, if alpha is 2, then 2x is the vector twice the size of vector x, which is in the same direction as of x. This is illustrated in the figure. Linear combination, span and basis. Almost all notions that we define make sense in a more general setting of vector space. However, we will not go into this generality, but restrict ourselves to only the most concrete vector space R n. If V1, V2 up to Vm are elements of a vector space R n, a vector V equal to alpha 1 V1 plus alpha 2 V2 plus up to alpha m Vm, where alpha 1, alpha 2, alpha m are scalars, that is, they are real numbers, is called a linear combination of vectors V1, V2 up to Vm. If we take all alpha I is equal to 1 to m to be 0, we can express 0 vector as a linear combination of any collection of vectors. This is called a trivial linear combination. If S is a subset of Rn, is a given set, its linear span or simply span denoted by S in square bracket is defined as the set of all linear combinations of all the elements of S. That is, span of S is equal to the set of vectors alpha 1 V1 plus alpha 2 V2 plus up to alpha m Vm, where V1, V2 up to Vm are in S and alpha 1 up to alpha m are in R. Examples: 1. If S is equal to E1, which is equal to 1 0, is the singleton set span of S equal to x axis. This should be clear from x comma 0 is equal to x into 1 0 is equal to x E 1. 2. If t is equal to E 2, which is 0 1 is the singleton set, span of t is equal to y axis, which follows from 0 y is equal to y into 0 1 equal to y E 2. 3. If u is equal to u 1, which is equal to 1 0 and E 2 equal to 0 1 is the doubleton set, the span of u is equal to R 2. This follows from the simple observation x y is equal to x into 1 0 plus y into 0 1, which is equal to x E 1 plus y E 2, linearly independent set. A set V 1 V 2 up to V m is called linearly independent set if 0 can be expressed only as a trivial linear combination of these vectors. In other words, no non-trivial linear combination of these vectors is the 0 vector. That is, if alpha 1 V 1 plus alpha 2 V 2 up to alpha m V m is equal to 0, then alpha 1 equal to alpha 2 up to alpha m all are 0. A set which is not linearly independent is called linearly dependent. That is, in this case, some non-trivial linear combination of given vectors is equal to a 0 vector. Examples: S is equal to E 1, which is equal to 1 0, E 2 equal to 0 1 is a linearly independent set, as alpha 1 E 1 plus alpha 2 E 2 equal to 0 0 implies alpha 1 alpha 2 equal to 0 0, which implies alpha 1 equal to 0 and alpha 2 equal to 0. 2. S equal to V 1, which is equal to 1 1, V 2 which is equal to 2 2 is linearly dependent as 2 times V 1 minus 1 times V 2 equal to 0 0. That is, a non-trivial linear combination of vectors from S is a 0 vector. Basis: a subset of R n is said to be a basis for R n if it is a linearly independent set and it also spans the whole space R n. Example: 1. U equal to E 1, which is equal to 1 0, E 2 equal to 0 1 is a basis of R 2. 2. S equal to E 1, which is now 1 0 0, E 2 which is now 0 1 0 is not a basis of R 3, as span of S will only be the xy plane in R 3 and not R 3. Scalar product or inner product and orthogonality. Suppose x is equal to x 1, x 2 up to x n and y is equal to y 1, y 2, y n, they are in R n. Then scalar product of x and y, which is denoted by x dot y or inner product x y, is defined as x dot y, which is equal to inner product x y, which is equal to x 1 y 1 plus x 2 y 2 up to x n y n. Two vectors x y in R n are said to be orthogonal if x dot y is equal to 0. Example: E 1 equal to 1 0 0 and E 2 equal to 0 1 0 are orthogonal vectors, as E 1 dot E 2 which is equal to inner product E1 E2 is equal to 1 into 0 plus 0 into 1 plus 0 into 0, which is equal to 0. We note that this coincides with our usual notions, matrices. We have considered earlier demand and supply functions of single commodity. In practice, generally demand and supply of any commodity depends on demand and supply of several other commodities. Example: suppose we have two commodities whose demand and supply are given by, for the first commodity, suppose the demand of the first commodity as a linear function of prices of two commodities is described by Q D1 is equal to A2 P2 plus A1 P1 plus A0. Suppose the supply of the first commodity as a linear function of prices of two commodities is described by QS1 equal to B2 P2 plus B1 P1 plus B0. Similarly, the demand and supply of the second commodity as linear functions of prices of two commodities are described by QDT equal to alpha 2 P2 plus alpha 1 P1 plus alpha 0 and QS2 equal to beta 2 P2 plus beta 1 P1 plus beta 0. As we know, absence of excess demands for the two commodities provides market equilibrium, that is EI, which is identically equal to QDI minus QSI, which is equal to 0 for I equal to 1 and 2. Hence, algebraic simplification leads to the equations A2 minus B2 into P2 plus A1 minus B1 into P1 plus A0 minus B0 equal to 0 and alpha 2 minus beta 2 into P2 plus alpha 1 minus B1 into P1 plus alpha 0 minus beta 0 equal to 0. To get the elegant form, we introduce new constants Ci identically equal to Ai minus Bi for I equal to 0, 1, 2 and gamma I identically equal to alpha I minus beta I for I equal to 0, 1, 2. On substitution, we get C2 P2 plus C1 P1 equal to minus C0 and gamma 2 P2 plus gamma 1 P1 equal to minus gamma 0, which are called two simultaneous equations in two variables P1 and P2. In standard variables, two simultaneous equations in two variables are written as Ax plus By equal to C and alpha x plus beta y equal to gamma. When there are m equations in n variables, they are written as A11 x1 plus A12 x2 up to A1n xn equal to B1, A21 x1 plus A22 x2 plus A2n xn equal to B2 up to AM1 x1 plus AM2 x2 plus up to AMM xn equal to Bm. Now, we are in a position to define a matrix with proper motivation. If we look at these equations closely, we immediately understand the three types of entities are involved. First, there are coefficients Aij which are mn in numbers. Secondly, there are n variables x1, x2, xn and m numbers b1, b2, bm. To manipulate these entities efficiently, matrices are at our service. So, we formally define matrix as simply an array of entities, usually of numbers and variables. A general matrix of m rows and n columns is written as A square bracket Aij, which is equal to A11, A12 up to A1n, A21, A22 up to A2n, up to AM1, AM2 up to AMN. For I equal to 1, 2 up to m and j equal to 1, 2 up to n. Often, instead of square brackets, round brackets are also used. We also note, as in the case of vectors, that two matrices are equal if and only if their corresponding entries are same. That is, if A equal to Aij and B equal to Bij are two m cross n matrices, which is read as m by n matrices, that is, they are of the same type, then A equal to B if and only if Aij equal to Bij for all I equal to 1, 2 up to m and j equal to 1, 2 up to n. When A and B are two matrices with real numbers or complex numbers as entries and of the same type, they have m rows and n columns, that is, they are m by n. Then they are added as A plus B equal to Aij plus Bij equal to matrix Aij plus Bij. That is, ith row jth column element of the first matrix is added to the ith row jth column of the second matrix to form the ith row jth column entry of the matrix A plus B. Scalar multiplication. If a matrix A is equal to Aij and alpha in R are given, we define scalar multiplication as alpha A equal to matrix alpha Aij, which means alpha is multiplied to every entry of the matrix A. Multiplication of two matrices. Suppose we are given two matrices A and B. The first matrix A is m by k and the second matrix B is k by n. Then the product AB is the m by n matrix whose general term Cij is formed by multiplying the corresponding terms of the ith row of A and jth column of B, both of which are having k entries, and then summing up these multiplied terms. That is, C equal to AB equal to Cij, where Cij is sum of AIL BLJ, L is from 1 to k. A special case can be visualized as zero matrix and identity matrix. A matrix A equal to Aij of the type m by n, all whose entries are 0 is called a zero matrix. A matrix A equal to Aij of the type n by n, that is a matrix with equal number of rows and columns, is called a square matrix. For a square matrix A equal to Aij of the type n by n, the terms Aii, I equal to 1, 2 up to n, are called main diagonal terms. If in a square matrix all terms on the main diagonal are identity, that is 1, and of the main diagonal all the terms are 0, then the matrix is called the identity matrix. This matrix is usually denoted by I, that is, I is equal to Aij equal to 1, 0 up to 0, 0, 1 up to 0, up to 0, 0 up to 1. For I equal to 1, 2 up to n and j equal to 1, 2 up to n, which can also be written as I is equal to a I j, where a I equal to 1 for I equal to 1 up to n, and a I j equal to 0 for I not equal to j, I and j from 1 to n. This matrix has interesting property, namely a I is equal to I a equal to a. This follows as the ith row jth column term in a I is formed by summing the corresponding multiplied terms from the ith row of A and the jth column of I, and the fact that jth column of I has all terms 0 except the jth term. Thus, the only surviving term in the sum will be a I j. Hence, a I equal to a. Similarly, I a equal to a. Transpose of a matrix. Transpose of a m by n matrix A equal to a I j is a n by n matrix A t equal to a j I. That means, jth row ith column entry in A t is ith row jth column entry of A. In other words, the rows of A are made columns of A t. Elementary row column operations. The matrix operations of 1. Interchanging two rows or columns, 2. Adding a multiple of one row or column to another row or column, 3. Multiplying any row or column by a non-zero element are known as elementary row column operations. These operations are important. They are used to transform the original matrix into a matrix having definite simple form. Also, certain properties of the original matrix and the transformed matrix remain invariant or are related. If the transformed matrix has simple desired form, and if the definite entity can be found out for it, we have got the entity for the original matrix also. This is the main use of these operations, row and column vectors. Given a m by n matrix A equal to a I j, it can be looked upon as made up of m many row vectors a I 1, a I 2 up to a I n. I is from 1 to m, which are elements of R n. These row vectors may also be called n vectors. Similarly, A can be looked upon as if it is made up of n many column vectors a 1 j, a 2 j up to a m j, j equal to 1 up to n, which are elements of R to the power m. These column vectors may be called m vectors. It is convenient and very natural to visualize these vectors as a 1 j, a 2 j up to a m j. These vectors can also be regarded as appropriate matrices. Row vectors mentioned above are 1 by n matrices and column vectors are m by 1 matrices. Now, we go back to simultaneous equations. Note that now we can write the equations a11 x1 plus a12 x2 plus a1 n x n equal to b1, a21 x1 plus a22 x2 plus up to a2n x n equal to b2 up to am1 x1 plus am2 x2 plus am n x n equal to bm, as the matrix A multiplied to a column vector x1 x2 up to xn equal to column vector B1, B2, Bm, which is same as Ax equal to B, where A equal to matrix Aij, x is the column vector and B is the column vector B1, B2 up to Bm. Soon we will use techniques of matrix algebra and discuss about the solution of simultaneous equations. Now, we shall talk about symmetric, orthogonal and idempotent matrices. A n by n square matrix A equal to Aij is called symmetric if Aij equal to Aji for all ij equal to 1, 2 up to n. That is, A is symmetric if A equal to At. Examples: 1, 2, 2, 9, 1, 4, 5, 4, 2, 6, 5, 6, 3, 1, 2, 3, 4, 2, 1, 7, 9, 3, 7, 8, 6, 4, 9, 6, 7 are symmetric matrices. A n by n square matrix A equal to Aij is called an orthogonal matrix if At equal to I. Example: A equal to 1 upon square root 2 minus 1 upon square root 2, 1 upon square root 2, 1 upon square root 2 is an orthogonal matrix as At equal to 1 upon square root 2 minus 1 upon square root 2, 1 upon square root 2, 1 upon square root 2 and multiplied by its transpose, which is equal to, by matrix multiplication formula, equal to 1 0 0 1. The length, often called norm, of a vector x equal to x1, x2 up to xn in Rn is defined as norm of x equal to norm of x1, x2 up to xn is equal to positive square root of x1 square plus x2 square plus xn square, which is the distance of the point x from origin of Rn. We note that matrix A is an orthogonal matrix if and only if its column vectors are unit vectors. That is, their lengths are 1 and any two distinct column vectors are orthogonal. Similarly, matrix A is orthogonal matrix if and only if its row vectors are unit vectors, that is, their lengths are 1 and any two distinct row vectors are orthogonal. A n by n square matrix A equal to Aij is called idempotent if A square equal to A. Example: A equal to 1 0 0 0, A square equal to 1 0 0 0 1 0 0 0 equal to 1 plus 0 0 plus 0 0 plus 0 0 plus 0 equal to 1 0 0 0. Thus, A is an idempotent matrix. Of course, zero matrices and identity matrices are idempotent matrices. We shall look at some more aspects of matrices and their applications in the next module. Let us summarize. We here started with the definitions of addition of two elements of Rn and also of scalar multiplication. We then listed down important properties of these operations, which actually form the basis of an abstract, that is, axiomatic definition of vector space or linear space. We have also conveyed geometric representation of vectors and the interpretation of vector addition and scalar multiplication. Then after, we covered with examples the notions of linear combination, linear independence, linear dependence, linear span and basis. We also discussed scalar product and orthogonality. Lastly, we introduced matrices with motivation from simultaneous equations. Operations of addition, multiplications were discussed with care. We have also discussed symmetric, orthogonal and idempotent matrices.